All right, so I'm going to go over the homework for the periodic trends problems. But before we do that, I want to go over like periodic trends in general. There are 4 periodic trends that you need to know for the AP exam. The most important one is atomic radius. And I'm going to put ionic radius on here, though it's not as important right now. It will be when we start studying ionic compounds. The next one is ionization energy. Oops, and G, can't write today. Electron affinity, which I'm putting on here. However, you're very rarely going to be asked questions on it directly. And then the last one, which is very important, especially as we go into our next unit, is electronegativity. Now, in the AP exam, you're going to want to memorize the trend, but you're also going to want to have a solid explanation as to why. And so I'm going to go through each trend with you guys just to make sure you're pretty clear about what the trend is and how you can tell me why one atom might be bigger or smaller than the other. All right, so here's a blank periodic table. We'll start with atomic radius. And the trend is that as you go across the periodic table from left to right, atomic radius decreases. Now the reason for this is if you're comparing elements in the same row, they have the same number of energy levels that you're putting electrons into. The difference is, though, as you go across the periodic table, the number of protons in the nucleus is increasing. So the nucleus is just getting a stronger core charge associated with it. And so as an example of that, let's say you had lithium. Now lithium is in the second row of the periodic table right there. And then I was comparing it to, say, fluorine. They both have 2 energy shells. And I'm using the Bohr model here to demonstrate this, though this is not the best one to use. But they both have configurations that end in the second energy level. The difference between the two, though, is this only has 3 protons, whereas fluorine has 9 protons. And so those 9 protons create a stronger core charge, which brings the electrons in closer to the nucleus, thus making the atom smaller. So remember that when you're comparing atomic radius, that's the main reason why. Now as we go down a group on the periodic table, let's go down this way, the trend is that atomic radius increases. And the reason for this is every time you go down a new box on the periodic table, down one group, you are adding a new energy level to that particular atom where you're putting electrons in. And naturally, those energy levels are further and further away from the nucleus, which is why the atom is getting bigger. So remember the trend, and again, remember why. If you're comparing elements in the same row, it's decreasing because you have an increased effective nuclear charge or core charge. And then going down a group, you have extra energy shells of electrons, which is making the atom a lot bigger. Now the next one we want to go over is ionization energy. Let's erase all this. So ionization energy is a very important trend. One thing you want to not get confused by is if it says first ionization energy versus, boy, I keep doing the exact same spelling on that. Energy. Versus saying like another number in front of it, like third ionization energy. So when we say first ionization energy, we're saying, well, how much energy does it take to remove the first electron from that atom? The third would be the energy required to remove the third electron. So this is assuming that you've removed 1 electron already and then a second electron. Now we're getting to a third. So that's what these numbers in front represent. Now back to the trend though. Now this trend is opposite of your atomic radius trend. And this is where you want to start using that whole Coulombic effect thing that we've been talking about in class. So ionization energy. So the trend is, as you go across the periodic table, we have ionization energy increasing. Well, why is it increasing across a row on the periodic table? Stronger Coulombic attraction. Why is there stronger Coulombic attraction? It's because there are more protons in the nucleus. We saw with Coulombic attraction that when you have more protons, the Coulombic attraction, or the force of attraction, increases as a result of that. Going down a group, ionization energy decreases. Now remember, elements in the same group have the exact same core charge. You guys saw this with your POGL. And so as we go down a group, electrons on the outside of that atom are getting further and further away from the nucleus. And so again, Coulombic attraction is very weak at that point. Because remember, as distance increases between a proton and an electron, the Coulombic attraction goes down as a result of that. So that's ionization energy. So that's an important one to remember. The next one is electron affinity. Now the definition of that is how much energy is released when an atom gains an electron. We want atoms to lose energy as much as possible, because the more energy that they lose, the more stable they are. Okay, so if you have an element that releases a lot of energy when it gains an electron, that means it probably really wanted that electron and has become more stable as a result of that. Now the trend is, so let's write this trend out so we can see it, electron affinity. The trend is the exact same trend as ionization energy. Electron affinity increases across the periodic table. And this makes sense. We talked about in class that elements on this side of the periodic table do not like to gain electrons. They like to lose electrons. So if you had, say, sodium, and you tried to add an electron to that, it probably would require energy to do so, not release energy, because sodium does not want another electron. Compare that over here with chlorine. Remember, chlorine has 7 valence electrons. It wants to get to 8. Adding 1 electron is something that it wants to do, so it's probably going to release a lot of energy as a result of that. Okay, so electron affinity, it increases. Elements that have high electron affinities really want those electrons. Erase that a little bit so we don't get it all messed up. Going down a group, electron affinity decreases. Again, all these are tied to Coulombic attraction. Okay, the farther away the electrons get from the nucleus, the less those atoms want to gain an electron, because the Coulombic attraction is just so weak. It won't be able to attract electrons very easily. Contrast that with going across the periodic table. It increases over to this side of the periodic table because Coulombic attraction is very strong. Okay, you've got small atoms over here. They have a higher core charge, more protons in the nucleus, so you're going to see that they have a better ability to attract electrons. Now the last periodic trend is electronegativity. And I would say pretty often students confuse electron affinity and electronegativity. So electronegativity has to do with the attraction that an atom has for a shared pair of electrons. So you have to imagine that there's another atom next to this atom, and they are sharing electrons. How much is this particular atom going to be pulling the electrons towards itself? Kind of like a tug of war. And this is a super important periodic trend, especially as we go into next unit. I know I've already said that, but can't stress it enough. Here's the trend. Electronegativity, just like the other two I just talked about. So electronegativity increases. Why? Stronger Coulombic attraction over here. Okay? Things that have strong Coulombic attractions are able to attract electrons fairly easily. So if you were sharing electrons with another atom, they'd be pulling the electrons closer over towards itself. Going down a group, electronegativity decreases. Why? It's because you've got a weaker Coulombic attraction as you go down these groups. Weaker Coulombic attractions mean you're not able to attract electrons as easily because the electrons are so far away from the nucleus at that point. So remember, on the AP test, if you were doing a free response question and they were asking about periodic trends, part of the answer would be requiring you guys to justify why you're choosing one atom to have a higher ionization than another, or why one atom has a lower electronegativity than the other. And it really all comes back to Coulombic attraction. It's super important to remember. All right, so to do the homework questions now. So we're going to start with question 105. And this particular question is asking us about increasing size, which means they're asking us about atomic radius. So for part A, we have tellurium, sulfur, and selenium. Let's find those three first. So we've got tellurium right here, selenium, and then we've also got sulfur. So this is convenient because all three elements are in the exact same group. So the trend we want to know here is that as you go down a group on the periodic table, atomic radius increases. Again, the reason why is as you go down a group, you are adding energy levels to the atom, and those electrons are getting further and further away from the nucleus. So if I'm going from smallest to biggest, I'm going to start with sulfur, and then we're going to go down, we're going to go to selenium next, and then we're going to end with tellurium. For B, we are comparing potassium, bromine, and nickel. So again, you want to find those on the periodic table. And so for those three, we've got potassium right here, we've got bromine right here, and we've got nickel right here. So conveniently, all three of these are located in the same period on the periodic table, the fourth period. And so we're going from smallest to biggest. Atomic radius decreases as you go across a period on the periodic table because you have an increased core charge, right? If elements are in the same row together, they have the same number of energy shells where we're putting electrons. This is the fourth period, and so every element there has 4 energy shells in their ground state configuration. So the smallest of all of these atoms is going to be bromine. Next one's going to be nickel. And then lastly, we're going to have potassium. For part C, now we are comparing a new set of elements. Again, you want to find these three on your periodic tables first. So we've got barium, which is right here. We've got silicon right up here. And we've got fluorine. So these are kind of going in like a diagonal pattern generally. So we're going to be putting together both sets of trends for a group and a period to answer this question. So if we're kind of following a diagonal type trend, you're going to find very, very large atoms down on this side of the periodic table and very, very small atoms on that part of the periodic table. So if we're going with that kind of general diagonal trend where we're combining both, our smallest atom here is going to be fluorine. Okay, it's got the least number of energy shells of electrons, and it's got a pretty high core charge. Next will be silicon, and then the largest of these atoms would be barium. Barium is in the 6th period of the periodic table. It's got 6 energy shells. That's a very, very large atom right there. So number 107 is a continuation of number 105, but now we're doing increasing first ionization energy. So again, that's the energy required to remove the first electron from an atom. And so again, we're going through the same kind of 3 elements we were in the previous problem. For part A, we're comparing tellurium, sulfur, and selenium. So again, find those elements on your periodic table. These 3, again, were in the exact same group. Now, the trend for ionization energy as you go down a group is that ionization energy decreases. So I'm going to start with tellurium first, then selenium, and then sulfur. The reason why is it's harder to remove elements from smaller atoms here because of Coulombic attraction. Sulfur has the least amount of energy shells, so the electrons are closer to the nucleus than, say, the valence electrons for tellurium. So stronger Coulombic attraction means it's harder to move electrons. For B, we are now looking at, let me erase what we have here first. So we are comparing potassium, nickel, and bromine. So we're going across the periodic table. The trend for ionization energy is, as you go across the periodic table, ionization energy increases. So if we're going in order, we're going to start with potassium this time, then nickel, then bromine. Bromines is so much higher compared to potassium because they're in the same row. So they have the same number of energy shells of electrons. But bromine has a much higher core nuclear charge than potassium does. So much stronger Coulombic attraction. Last question. We're going to go in that diagonal type pattern again like we did earlier. And so we are comparing barium, silicon, and fluorine. So if we're going diagonally, the largest atoms are going to have the lowest ionization energies because of that weak Coulombic attraction. So barium's going to be first, then silicon, and then fluorine will have the highest first ionization energy. Okay, question 121 says to order the atoms in each of the following sets from least exothermic electron affinity to the most. That's a really fancy way of saying go from the smallest electron affinity to the highest. So we're choosing between just two elements in part A. We're choosing between sulfur and selenium. Sulfur and selenium are in the exact same group. Okay, so remember, electron affinity trends follow the same kind of pattern as ionization energy. Smaller atoms have higher electron affinities. Remember, smaller atoms have a stronger Coulombic attraction for electrons. And so that's what's going to create a greater electron affinity. So I'm choosing between sulfur and selenium. I'm going with the least, so it's going to be selenium in this problem. And then part B, we're choosing between 4 different elements. All 4 of these are the halogens, so they're in the exact same group together, right over here. Again, we're choosing the least exothermic to the most. Well, I guess in the last problem, I should probably do that. So if I'm going from least to greatest, remember smaller atoms have high electron affinities. Larger atoms down here, like iodine, have very low electron affinities. So we're going to basically start at the bottom and work our way up this group from least to greatest. And there's our answer. So for this last question, you guys had to jump to page 405, question number 27, which is on electronegativity. And we're going from smallest electronegativity to greatest. So just like we've been doing, you need to find the 3 elements in this question on your periodic table. C, N, and O are all next to each other in their same period. Remember, electronegativity increases as you go across the periodic table. So following that trend, we're going to start with carbon as the least electronegative, then nitrogen, all the way up to oxygen. Again, all this is due to Coulombic attraction. As you go across the periodic table, Coulombic attraction is increasing in a period because you have an increasing number of core nuclear charge. For part B, we've got sulfur, selenium, and chlorine. So we're going to go find those. Sulfur, selenium, and chlorine are kind of like these 3. So if we are going from least to greatest, I'm going to choose the bigger of all these atoms first. Bigger atoms have low Coulombic attraction, so selenium is going to be the least electronegative. We're going to go up the group. Remember, as we're going up a group, electronegativity will be increasing, so sulfur would be next. And then across from sulfur, right next to it on its side, is chlorine. Chlorine's going to have a higher electronegativity because it has an increased core nuclear charge. Greater Coulombic attraction there. For part C, we are comparing, we're going to erase these guys. So we are comparing silicon, germanium, and tin. All those are in the same group together. So as we're going down this group from silicon down to tin, electronegativity is decreasing. So from smallest to largest electronegativity, we're going to go tin first, then germanium, and then silicon to end it. Lastly, we've got thallium. So right here, we've got sulfur, and then we've also got germanium. So we're kind of going in this diagonal type pattern. And again, big atoms have very weak Coulombic attraction, so their attraction for electrons is going to be very, very small, and their electronegativity will be low as a result of that. So Tl is going to be first. Then we're going to go germanium, and then up here to the smallest of these atoms, which is sulfur, and that's going to have the highest electronegativity. That's it for the homework. If you guys have any questions, come see me in class.